In this video, we're going to finish the concepts of chapter 7. Now we are going to explore energy in chemical reactions. In order for chemical reactions to happen, understand that there are three conditions that must be met. That is, first, the reactants must collide. There has to be a collision, meaning the two reactants must meet. Next, there's a particular orientation that these two reactants need to meet each other. They need to align properly because that's what's going to lead to the breakage or the formation of bonds. Lastly, energy is involved when these collisions are happening. It must provide specifically energy of activation, or in other words, activation energy. The way that we illustrate um, the the diagrams or the reaction progress for a chemical reaction is in a chemical reaction diagram, which is what we see illustrated right here in the bottom. We can observe that this energy of activation is basically the energy that the reactants must achieve in order to form the transition state, which is the top of the peak, in order for them to produce the product. In order for reactions to happen, we can observe that either energy is going to be consumed or energy is going to be released. And we have terminology for these two processes. When it comes to the energy and chemical reactions, if you have a reaction in which heat is released in order for the reaction to occur, that is actually known as an exothermic reaction. What that means is that heat is exiting the system. So that's why we see the energy in the product side of my chemical reaction, because that energy in the form of heat is a product. In addition, when we look at a reaction that is exothermic, the energy of the products is less than the energy of the reactants. And then we can see that illustrated here in the energy diagram. Next, we have processes in which energy is not released, but energy is absorbed. So this heat energy that is absorbed results in a reaction that is called an endothermic reaction. When it comes to endothermic reactions, because the system is absorbing heat, heat is going to be in the reactant because it's been added to the system. So we can see it here in the following chemical reaction, how the heat is added to the reactants. Lastly, when it comes to the energy comparison between reactants and products, we can observe that the energy of the products is actually greater than the reaction, that the energy from the reactants. So the energy of the products, you can see that it is higher compared to the energy of the reactants. Reactions that are going to happen can occur under exothermic reaction conditions or endothermic reaction conditions. So understand that this is just a particular observation of a reaction. It's not to be said that all reactions are exothermic or all reactions are endothermic. They are going to proceed in the way in which they can release heat or they will absorb heat, and that can only be done in the laboratory. The last thing that we're going to mention is specifically what is the rate of the reaction? Because so far we have only looked at energy being absorbed or released, but it tells us nothing about the rate of the reaction, meaning the speed in which we have a change from reactant to product. The reaction rate for a chemical reaction is a measure of the change in the concentration of the reactants or the change in the concentration of the products per unit time. And when it comes to chemical reactions, there are things that actually affect the reaction rate. All of those observations are summarized in table 7.4. What we have here as an example is an energy diagram specifically for a reaction in which the lavender line is going to give us a reaction that has been catalyzed, and I explain in a moment what that is. And then the regular reaction is actually given by this blue line, okay? So how do we change the rate of the reaction? We can see that we can increase the concentration of the reactant. And in a way, that makes sense. If you had more reactants, more collisions are going to happen. Another way in which we can increase the rate of the reaction is increase in temperature. Because what happens is that in the increase of temperature, then there are more collisions because there's increased kinetic energy in the reactants, and those more collisions are going to lead to having an activation energy that is going to get those reactants into products. But the image that we have here has to do with the addition of catalysts. And a catalyst always leads to an increase of the rate of the reaction, but it does it by lowering the energy of activation. So let's go back to our energy diagram. If specifically, my reaction is this blue line that I'm just making it thicker to observe it. If I run the same reaction with a catalyst, we can observe that specifically the energy of the reactants and the energy of the products is not changed. The only thing that happens is that a catalyst is going to reduce the activation energy. So the energy that has to be overcome to produce the transition state, then to lead to the production of product is lower. And by doing that, it's giving you a route that basically is, in a way, shortening the distance to go from reactants to products. But in chemical terms, that will be just a decrease in activation energy in order for the reactants to form products at a faster rate.